Welcome. Normally, I don't do this, write something on the board or display some printed matter and explaining with a stick. Normally I don't do this because I don't think that is as effective as actually writing it while explaining. But unfortunately, I resorted to this mechanism, and that will be only for a short duration of the next 10-15 minutes. Because since we are paying homage to these mathematicians, super brains, I should call each of them, I don't want to miss a single name. So I made the list. In fact, it is a good exercise for you people to read about these people's history. Everything is documented. Historians have gone into a great deal of research to figure out when was Brahmagupta born, or when did Aryabhatta write Aryabhatiya and so on. So they've taken a lot of trouble, and all the documented literature is available at your fingertips. And Wikipedia is one of the best sources that I have found. And in fact, I have discovered these from that only. So there's nothing, it's not something which I suddenly found out one day. So it's not like that. I suggest each of you go through those. One problem with Wiki is that it is a HTML document. What is an HTML? Is hypertext markup language. That means whatever text is there is almost looks like the board, but it's not quite like the board. Some words will appear in a slightly different color, and if you click on those words, it opens up. It's like a hole. It opens up another document. So you got an original document of 4 pages, and it will probably contain hundreds of such words, each of them opening into their own respective 4 pages, which again contain hundreds of words which can again open. So it is a nested series of documents, and to trace it is a bit difficult, and we lose track of what we are doing in the first place. Once you track a couple of words like this and go inside the story, now you are reading about something else. You are talking about war in Europe or something. Suddenly you say, my goodness, I was actually reading about mathematicians, and where did I get landed up here? So that means you have to be very careful when you read this Wiki document, because of its the nature of the way it is presented. Of course, the presentation is one of the best way of presenting that much of a huge amount of literature. Thousands or millions of pages of text has been presented to you, and the index is you are pressing via those words. That is the index. There is no separate index for it. So is there. So you will have to take a bit care there, but I suggest you go through this. And I was tracing. See, now you can see each of them has a history of why they became a mathematician, or how they discovered some things or invented a few things and so on. Is there. That itself is a bit interesting to us, just to figure out. But then what was my main interest in this is to follow 2 storylines actually. I was just trying to figure out 2 storylines to see could mathematics in general and science in particular, or rather the other way around, could have evolved much earlier than the period that I have mentioned. So because of the discoveries which are made earlier, but unfortunately was not used. So because we see hundreds of years of gaps between 2 developments. So I was wondering why it happened. That is one of the storylines. Where it got missed, I would like to show you that. And the second is one of the main pressures under which almost every human being works. Even you, me, everybody. We have the social pressure of satisfying our relatives and our neighbors and so on. Then we have political pressure, which is much more important. In the early days, I think political pressure was the maximum effect on the way people worked. Some people could not work because of political situations. One example is Copernicus. I have not mentioned his name here because he is remembered more as a physicist rather than a mathematician. And Copernicus proposed the heliocentric theory of planets revolving around the sun. Of course, that idea was there earlier in the Greek legends also, but he presented a more coherent picture of that, which was definitely against the church. Because church always sincerely believed that earth is the center of everything and everything revolves around the earth. This is the main thing. So obviously they didn't like that. And the church had a much greater influence on the politics than what it is today. Church was actually bigger than the king, so in those days. So obviously they excommunicated Copernicus, so he couldn't even work. First thing. Second thing, they called on Galileo, one of the fellows who discovered the telescopes and actually confirmed the theory of Copernicus, told him to give an official statement saying that what Copernicus is saying is nonsense. Now you can see the amount of pressure the political environment can put on people. So there are two storylines that I wanted to follow. That is one aspect. Now the second aspect is we would like to greatly remember some real greats in this. All of them are great, there is no question on that. So obviously they will beat the hell out of any one of us. Absolutely no questions on that aspect, each one of them. But there are some specials, even in these special people, which people remember as having contributed to probably 90% of what science has evolved today. Of course, goes without saying, I won't even talk too much of Newton because he's just too great. And Isaac Newton did discoveries in physics, in astronomy, in mathematics, in optics, and you name the subject. In fact, some historian says that at that point of time in 16XX Christian era, whatever subjects of mathematics and science were known, and Newton were responsible for taking them forward by leaps and bounds. Each one of those branches, every branch which was known, at such a greatest of the great, what do you call them? Badshah ka Badshah, that is Isaac Newton. Then, next name which comes to mind as one of the greatest mathematicians, Leonhard Euler of 18th century and one of the greatest of all times. So he probably started new branches of mathematics. He is the type of person. Newton may not have actually started a new branch, but Euler started many new branches of mathematics by his discoveries. I would like to talk about Euler as a special case of history of a person. Then the next person to him, the only next person who did equal number of, or at least close to the number of contributions Euler did was Cauchy. Augustine Cauchy was there. Then the last couple of names here are of interest to us because they introduced what you might call rigor into mathematics. See, many of the things Greeks did or Indians did or whoever did was more intuitive, saying, I'm going there, supposing I go out of this room, I'm outside. After 5 minutes, Shastry is outside the room, correct? So you might think, did I pass through this door? Yes or no? Simple question. No? Did I not? You would say yes, no. Obvious, there's no need to even state it. But then we have made an implicit assumption there, and that is actually called intermediate value theorem in mathematics. If you want to rigor, you have to assume that, that I must have passed through this door to reach the other side, A function, if you look at the plot of a function, I got the x-axis, what you call the independent variable, and for each value of x, I got a corresponding value for the function. We can plot the points of the function on the y-axis. What you get is some kind of a curve, right? So this is called a graph. When you write a graph for the function f, we find that for some values of x, this function f is negative, So like that. And for some values of at a later stage, that means between points, I am looking at points a and b on the x-axis. A and b, and here fa is negative. After some time, fb becomes positive. So we implicitly assume it must have passed through 0 there. 0. That is x-axis. That is known as the root of that function. That is the intermediate value theorem. Actually, it is a theorem. How do you assume it? Is one question. And we say, yes, it passes through or cuts across the x-axis at a point, and we define that point as one of the real values. See, that is the definition of real number system itself, assuming that any function which passes through that from negative to positive or positive to negative, must cut through a point which is also real. That is the assumption that actually we're making an assumption there that that point is a real number. No? So that is the intermediate value theorem. So now you can see that kind of rigor is required, and all of these people were so busy inventing new stuff in mathematics and science. Many times they worked more intuitively than on rigor. It's correct. There's no question. In fact, I will quote Euler straight away on this. Euler produced something like 886 research publications. That means, each of those research publications, supposing it didn't exist and you present it today to Bangalore University, tomorrow you will get a mathematics PhD. 100% guarantee. That's the quality of those research papers that he published. Each of them is that quality. So if you assume that Euler produced all this over a period of 10 years, not 1 or 2, 10 years. And 10 years, each year is 52 weeks. I just did a quick mental calculation. 10 years will be 520 weeks. So that means every 4th day, today one, next Thursday is next paper. Every 4th day he produced a new research paper which could get him a PhD in any university in the world. That is the quality of brain that we are talking about, to understand. So, really great person. So, obviously, every 4th day he is doing that, and he will have to make some intuitive assumptions. Otherwise, it's impossible for somebody to have that rigor, the mathematical analysis. These are all topics which he could not go into because he was more interested in the end result. Intuition is correct. We know Shastry passed through that door. It is correct. You can assume it for the moment. But wait, later on somebody has to prove that actually he did pass through the door. So that rigor has to be introduced. And these are the people who were responsible for that rigor to come back. Bolzano, number one, rigor man, in mathematical analysis. Weierstrass is another, his friend of his. And together there is one Bolzano theorem, there is a Bolzano-Weierstrass theorem, and so on. So all these. And Cauchy has also done a bit towards that rigor. So there is a Cauchy sequence also. So that means basically there are 4 fundamental assumptions that we make. All of them are equivalent in terms of real numbers. One is what is known as a Cauchy sequence convergence. Next is a Bolzano's theorem. That is the intermediate value theorem. Then there is a Bolzano-Weierstrass theorem, which says that an infinite bounded sequence must have a subsequence which is convergent. Means the same, actually it means the same thing. Then lastly we have what are known as nested intervals. I have not written that here. And if you have an infinite nested interval, it must converge. So one of these 4 assumptions has to be made. And then the rest of the mathematics becomes totally rigorous, and you can prove every one of the theorems with perfect clarity. So they're actually called axioms. Axiom, you can call them 1, 2, 3, 4. You have to assume one of them. It doesn't matter which one you assume. If you assume axiom 1, you can prove the other 3 using that. Or you can assume axiom 4 and prove the first 3 and so on. So you can go ahead and do that. I may not even actually do that assumption. I will use an intuitive way of constructing the real numbers, which is almost equivalent to Cauchy sequence. Okay. In fact, this Cauchy sequence, one of the reasons I listed Babylonians, let's come back to our story today. This is enough of personal detail. And maybe I should talk of, when we are talking of history of persons, how political pressure plays a role, we should talk of Leibniz also. See, there was, in 1711, there was a huge fight, official fight between Isaac Newton and Leibniz, saying, Newton said, before I published my papers on infinitesimal calculus, the manuscript was there, Leibniz must have seen that manuscript. He has published calculus, so he has stolen, like a plagiarism, he has stolen my ideas and published it before I could publish, because he must have seen my manuscript, because it's the same, it looks the same, the analysis looks the same. But that's not true. Actually, they finally officially proved that Leibniz independently did that work on calculus. And both of them are given credit for inventing calculus, right? Yeah, but that is a bit unfortunate if you ask me, because if you go back in history, we have one Bhaskaracharya. There are two Bhaskaras there. First Bhaskara 1, the other one is Bhaskara 2, also known as Bhaskaracharya. Bhaskaracharya proved that d by dx of sin theta or sin x is equal to cos x. He had already proved it. And you were talking of calculus, he had already found the derivative of a trigonometric function. Brahmagupta has already done it, And he conceived differential calculus, and he also gave formulae for sin a plus b, sin a minus b in trigonometry. He already given those formulae. Brahmagupta already gave those formulae in 650 CE. It took Newton and Leibniz 1000 years before they could latch onto it. Same way, we have Bhaskaracharya, or in fact, we have Brahmagupta himself introduced one term called Gurutvaakarshanam. I will write that in Devanagari script. Everybody knows what is Guru, no? Guru is weight or mass. Akarshanam is attraction. Actually, law of gravitation. That is actually law of gravitation. He proposed that in 650 CE, and it took suddenly Newton had to find one apple which falls on the ground. He's already told by our Brahmagupta 1000 years earlier. But we give Newton the credit for Newton's law of gravitation, one aspect. Nothing we can do about that. In that aspect, what was at fault? Was there nobody before Isaac Newton who could have discovered law of gravitation? Let's forget about Indians, because I think Indian people or Hindu people, they were more interested in non-materialistic things of life. They were not interested in materialistic things, so they never bothered. In fact, all the sin x, cos x, sin a plus b was of interest to them only because they wanted to construct those homakundalas or of square shape, round shape. Their interest was not in Newtonian mechanics or whatever, so obviously their interest was more non-materialistic. So let us assume they were not interested. But there must have been others who were interested in Europe who could have discovered these maybe at least a few hundred years earlier. So what is the reason? The reason is translation, I would say, I think was translation errors or whatever. See, when somebody translates, remember all these people of Europe, when they got look at the Indian mathematics literature, there was a double translation. There was an original translation from Sanskrit to Arabic, because it was basically a Muslim world in Europe with Ottoman Empire and all those occupying forces. And from Arabic it has to be translated to Latin, and somebody had to learn Latin, even though it was not a spoken language, to even study those documents. So there are two translators involved here. So there is a Muslim translator who has to learn Sanskrit properly and translate it to Arabic. Maybe his version of Arabic is perfect, but he might have missed something in original Sanskrit, possible. Then somebody else, probably an Italian person, has to translate that Arabic back to Latin, and his knowledge of Arabic might not have been so great to write home about. I still recall in our village, there was one gentleman, his name is Ganesh Sharma. He is no more. And we all grew up reading Bengali stories by Rabindranath Tagore, not even Tagore, Sharat Chandra Chatterjee, so some great stories he has written. But unfortunately, he wrote all those stories in Bengali only. So obviously, we needed somebody to have translated that. We didn't even know Hindi. First translation was to Hindi. And from Hindi, a second translator had to translate that to Kannada. And we read that in Kannada. And some were directly available in English also. Once we learnt English, we could read the English translation of the original Bengali also. And this, our friend Ganesh Sharma didn't believe, he always believed translators will always make a mistake, So he said, I must read this Sharashchandra story in proper way, the only way I can do that is to learn Bengali. So he learned Bengali. I still remember. He learned Bengali so that he could read. Only purpose was to be able to read Sharashchandra Chatterjee's novels. And after that, obviously, he read all of those novels in Bengali, and he did translate that, one of them, into Kannada before he died. Unfortunately, his command of Kannada language was not so good, so the translation is unreadable. There is only one exception that I have seen. One of the stories of Sharashchandra was translated to English by a Swamiji, one of the greatest translations I have seen. I have not seen the original, but reading this translation, you feel this must be better than the original. So that's the kind of quality. Unfortunately, I think it might have got missed there. Some of the important aspects, they may not realize that this Gurutvaakarshanam is some word mentioned in some poem there, the importance of that. They are more interested in the decimal arithmetic and algebra, the solution of quadratic equations, which are more practical. So this is non-practical, so nobody was interested. I think our Al-Khwarizmi, Al-Biruni and Al-Kashi, you can see that they're all Muslim mathematicians and historians. They are basically translators. I'm not sure they invented anything in mathematics by themselves. Doesn't matter. In fact, Al-Kashi, what he did was to take the decimal number system of India, Hindu-Arabic numerals, and then publish a huge treatise on what are called decimal fractions. Decimal fraction is a very simple thing to visualize. I'll just give you one simple example. Supposing you have 1.234 or whatever, what you do is you multiply and divide by power of 10 so that the dot disappears. So you can write the same thing as 1234 divided by 1000. You can write that as a ratio of two integers. Any decimal number can always be written as a ratio of two integers, right? So this is known as a decimal fraction. You can cancel a 2 or 3 or whatever and reduce it to the minimal ratio, or you can leave it as it is. So this is known as a decimal fraction. And Al-Kashi was excited about these decimal fractions. He wrote an entire book on it. Unfortunately, he published the entire thing saying it is mine, and he didn't give the credit to Bhaskaracharya or Bhaskara or actually given the decimal fractions, already given earlier. Doesn't matter. And our Simon Stevin is a lowly fellow in the case of mathematics, of course. He was interested in this decimal fractions, and he dealt with it, and he even published some papers on behavior of decimal fractions and how they do and so on. I think this has got something to do with the Cauchy's convergence also, Cauchy sequence convergence, which originally started from Babylonians. In fact, they had given an algorithm, numerical algorithm for finding square roots. Simple thing like that. It's a brilliant algorithm. In fact, yesterday I tried that algorithm on Microsoft Excel worksheet, and within 4 or 5 iterations it finds the square root of any number that you want, accurate to 10 decimal places. It's a super numerical algorithm, but actually that is a Cauchy sequence. You can see the difference of about 3000 years between the two historical events. That is different. So now Stevin gave a paper on this decimal fraction. I don't know how far he read Al-Kashi's literature or didn't read. We don't know the story there. But the reason is decimal fraction is a minor matter in mathematics, I know. The reason we mention that, anybody mentioned that, is because this was one of the great inspirations, apparently, in Newton's own words. He said, I was impressed or inspired by decimal fractions. So maybe it inspired him to do many things in life which he did do, of which we are all proud of. One of the reasons probably was this decimal fraction business. You can see the origin of that. That is one historical line that you can trace, so that is there. Other one, on the other history line, like I mentioned, was about the political pressures which Leibniz faced. Leibniz never wanted to be a mathematician. In fact, he was not educated for it. He was educated as a philosopher. Remember, philosophy was actually a subject. Unlike today, you could study philosophy at a graduate level. No? So then you become a philosopher, like a mathematician or a physicist, or you can become a philosopher. So, and in fact, he even became a professor of philosophy in one of the colleges. And he is known as probably one of the youngest professors of philosophy in the history. At the age of 19, he became a professor of philosophy. At the age of 19, remember, he finished his philosophy course and actually became a professor of philosophy at the age of 19, right? And I'm not sure philosophy was really of great interest to him. He was brought up by a stepmother or a foster mother, and the encouragement that he got from her apparently was, she was saying, you guys, you are philosophers, you worry your head all the time throughout your life so that somebody will remember you after you die, So that is the kind of encouragement, if you think, he got. That was actually not even his interest, but then you have to do something in life, right? So he became a philosopher. Then he wanted to get a government job. There were no other jobs as such. We say he's a German. Actually, remember, Germany as a country didn't exist. He's one of the German-speaking people, So some of the authorities of the German-speaking people, he wanted to get a job. He said, why don't you give me a job? And so on. Obviously, he said, no, we don't have a job to give you. Reason is very simple. Remember, French fellows, France, under the leadership of who is the most popular premier of France? Napoleon. Under the leadership of Napoleon had become very strong in Europe also. And those French armies, they were everywhere, and they were always troubling these German people. So these Germans were more worried about this current problem of what do I do when the French come, what do I do when he said, well, how can I give you a job? If this is the situation. Then he said, I got one brilliant idea how we can solve this. You give me a job, I'll tell you how to solve this French problem. How do you solve the French problem? He said, you take me to Napoleon. I'll go to Napoleon. I'll give him a proposal, and as per the proposal, you will be left alone, so that I have my job. Actually, his interest was only in his job. So he went to Paris. What was his proposal to Napoleon? He said, boss, fighting among ourselves. See, Europe was a problematic place in those days, because the tribes of Europe, they're always fighting among themselves. Now you can see, French were fighting with the British was fighting with Dutch was fighting with Portuguese, everybody was fighting with the Spanish, and they had this Ottoman is what? Osman I. That is the Latinized name of Osman I. Osman I was called Ottoman. So Ottoman Empire was there everywhere, and everybody is fighting, And why are they fighting? Because they want to get some resources, they want to get some gold, they want to get some material and so on, right? So that is the purpose. Then he told Napoleon, boss, we are like thieves, yeah. You are a robber, I am a robber, correct? I go and rob people, you also go and rob people. This is our business, primary business. Now, if we fight among ourselves, where is the honor? We don't gain anything. What do I gain? Nothing. You also don't gain anything. I will show you a nice place there where you can go and rob and mint money, mint. There's so much. What is that place? India. And currently, who is in charge of that? Who is doing that maximum robbing or pilferaging or whatever, plundering, whatever you want to call it, is the Dutch East Indies Company. So he told Napoleon, you go to Egypt, where they are ruling right now, conquer, do have a fight in Egypt with the Dutch, kill those fellows, then you get a direct route to East Indies, and that's where you get leave us alone. That time the British had become more powerful than French. French said, boss, Dutch, I've got my problems, don't even talk of Dutch and Indies and so on. So he had to go to London for that purpose. And in London, then he tried to contact the authorities. They said, we have got our Indies situation all right. We have our East India Company, Robert Clive and all those fellows are already there, so we don't need your advice, So, and then he didn't know what to do in London. He had a few friends who were mathematicians, and he got hold of some of those books they had kept there, read the mathematics, taught himself mathematics, at the young age of 20, and then invented calculus. So you can imagine the brain power of Leibniz. That is other storyline. But I suggest you read all these their histories on your own in Wikipedia to give you a bit of excitement for you. Okay? When we want to do the calculus discussion, I would like to just show you one small diagram, how they came up with the names for the trigonometric functions. It is not really important, but I thought that one particular diagram was so inspirational to me, I thought I should share with you, nothing more than that. Because I had a feeling till yesterday that they named these functions wrongly. What they are calling it as secant x should have been called cosecant, and what they are calling cosecant should have been called secant. Because I found you got a sine and a cosine. 1 over sine should have been secant, 1 over cosine should have been cosecant. In corresponding co, like that. Sine, cosine, secant, cosecant. I thought like that, but that's not correct. What they have named is correct. I'll show you why. Now this is a very simple diagram. We have seen this diagram earlier. We need an angle first to calculate the trigonometric function. I won't even bother drawing the angle completely. I will draw it in a dashed line. The reasons will become apparent to you as we go along. So this is the angle of interest to us. We can call it theta, you can call it A, whatever. I think we prefer to call it theta because it is not a triangle. If you have a triangle, you would call it ABC. So angle. So we are interested in the trigonometric functions of this angle. So now the method is to draw one perpendicular to the inclined line to intersect the horizontal line. So we drop a perpendicular. Now where on this line we drop it actually is immaterial because we are only discussing ratios of these side lengths. It can be anything. As an assumption, we will treat this length of the inclined line intercept as 1. We'll just take it as 1 so it becomes easier to calculate. And then we drop a perpendicular from the intersection onto the horizontal line. Now basically we got 3 line segments, one on the horizontal line from the point of the angle to the point of intersection. Then we've got the altitude, second line. Third is the third line. Now the reason we have drawn this perpendicular, because we have drawn the perpendicular, remember this distant 1, if I mark it on the horizontal line, it will be somewhere beyond this, right? The same distance will be beyond because this is perpendicular. And in fact, I can draw a circle. I mean, I won't actually draw it. I will start writing it. Because it is perpendicular to that line, this will be tangential. It's a tangent actually. So this line actually is a tangent. And now you can see the horizontal line is known as Chedika in Sanskrit. Because it intersects the circle in 2 points. When you say I've got a circle and a line, there are three possibilities. One is line is totally outside the circle, is an external line. And the second is a tangential line which intersects it at only one point. And third is a line which intersects it at 2 points. In English, normally is known as a secant line. This is known as secant line. So you got a secant line and a tangent line. Now here I have both. Secant line is Chedika. I got both here. This is the secant line, right? So we call it secant theta. The length of this line itself is secant theta. Then we got a tangent line and we call it tangent theta or tan theta. And as usual, opposite side by hypotenuse is sin theta. So hypotenuse is 1. Therefore, this opposite side, height of the altitude is sin theta. Very simple definition of these three functions. And now, where are the other three fellows? Now, cosine, cosecant, and cotan. Very simple. Now, if you look at this theta, and if I drop a perpendicular here at this point, I were to drop. Now, you can same way like I have this side triangle, I will get a triangle on the other side, upper side. There again you will have three lines there. So, cotangent theta, cosecant theta, and cos theta. That will be the perpendicular. On the other side, one way of looking at it. Another way I found is a simpler way. What I want is a co something, right? Co-jiva, co-cheda, right? And this is sparsha in Sanskrit, if you want all the names. Sparsh is touch. Tangent only touches, no? Whereas chedika intersects. So it cuts in two pieces. So this is chedika, sparsh, and sin theta is of course jiva. So these are names given by Aryabhata anyway, jiva, sparsha, and chedika. So they can't sin, tan, and secant. Now correspondingly we got the cosine theta right here in this triangle, but it's available in the other diagram also, because co of any of these functions, co of xxx of theta, that is cosine or cosecant or cotan, if you want, will be the corresponding function of the complementary angle, xxx of co theta. Co theta, in this case, there is a co theta right here. So this is a complementary angle because we are right angle triangle. No? Actually, this is also a complementary angle. Both are same. So of this, if you take the sine of this, or if you take the cosine of this, will be the sine of this. Sine of that will be cosine of this, and so on. You understand? So, sine and cosine. Similarly, cotan and tan of tan. Cotan of angle is tan of complementary angle. Cosecant of angle is secant of complementary angle. Cosine of angle is sine of complementary angle. So that's how you define those three functions. I think that it's not a big deal, but I found it interesting, so I wanted to share that diagram with you before we go on to the actual function, algebra of functions. So we'll go to the algebra of functions. Or before that, we can even look at, like I said, real numbers. Today, modern day with the rigor, they are defined using one of the four axioms. But I said we prefer using intuitive method. There are two methods there. One is the real line mapping. We call it real line itself because we are mapping real numbers as points of a line. That means that it goes both ways. If you say, I've got the set of real numbers, set is just a group now, the infinite number of them, of course. So this set is known as a real set, normally written as a stylized R. So is the real set. Similarly, natural numbers is stylized n, that's how we write. And rational numbers, they write it as a stylized r to represent rational number set. So we are saying that every one of these real numbers has got a unique point on the real line. Similarly, every point on the real line, distinct point, has got a distinct real number which is mapped. So it basically is a one-to-one mapping between real numbers and the points on this line, one line, which is, we call it the real line. Normally we draw it towards east so that we get two parts to it. We mark one position as 0. And we get to the left of 0, we also get infinite number of points towards west direction. And arbitrarily we say, to the right of 0, we have what are called positive real numbers, and left of 0 we get negative real numbers. That is one aspect, right? Then they are very dense. That means between any two real numbers, call them A and B, for example, doesn't matter how close they are. You will find infinite number of real numbers within that. Again, between every pair of those infinite numbers, you will find infinite number of real numbers. So it is so dense, So you can keep breaking that into smaller. And in fact, this is the principle of nested intervals. You start with one interval, then you have one more interval which is totally inside, which is a nested interval, either this side or that side or whatever that is. And within that you create a third interval, then the fourth, then the fifth, then the sixth, seventh. If you keep doing that indefinitely towards infinity, you will reach a place, and that point is a real number. That is the definition of the real system using nested intervals axiom. That is also an axiom which says that's how we reach. Any point in this I can reach by an infinite series of nested intervals. Is defined as a real number. So that is one more definition which people use, one more axiom, not definition, they give it as axiom. So that is one aspect. Second is real number is also known as a metric space. See, they have different kinds of spaces. What is space? It's not that space, it's just space. I mean, there is no definition for it, you have to assume. Take my word that metric space is space is a set of things which can be measured. That metric means measurement. Metering has got to do something with measurement. And here, what is the measurement in the real number system? Is the distance from 0. Itself is a measurement. Every real number has got a unique distance from that 0 point. And that distance, of course, you get positive and negative distances, is the measure of that number. So that is one. That's known as a metric space. And when you have metric space, we get one property, what we call order. They are ordered also. That means we have a real number B which has to be greater than A, if it is to the right of it. Or if it is not distinct, it can be in the same place as A, or it can be to the left, then we write less than A. So to be able to write less than, greater than, equal to is known as ordering. Real numbers are ordered, imaginary numbers are not. Like square root -1, is it less than 0 or greater than 0? Nobody can answer that. They are not ordered. There is no order to imaginary numbers, but real numbers are ordered. That is one property. And the second property is the closedness. Real numbers are closed with respect to a set of operations like addition, what is a plus, subtraction, multiplication and division, with one small caveat: division not permitted from 0. You can't divide by 0. Other than division by 0, we can do all these 4 operations on any two real numbers, A and B, and the result will also be real, will be in the same. So you do any kind of operation on two real numbers, you do the operation, and the result of the operation will result in a real number only. It cannot go outside. So that is known as closure property. Is closure. Order and closure are two important properties of this metric space, what we call real space. And our entire discussion of Functional algebra is based on this real system. There are other spaces. There is one more space which is called topological space, which may not have metric, which is not metric. There is no meter there. There are independent items. You can't measure them. And we can have a space of those items and discuss properties. These are basically sets. Sets. They're just sets of items. Then you could have some fields and so on. So these are all some advanced areas of mathematics. If you're interested, you could read. Some part of the sets theory is also brought into our calculus by our Bolzano and friends, Weierstrass, to achieve the rigor that is required. But unfortunately, you may not be covering that as part of your college education. So I'm not sure whether we are going to be discussing that or not. So I am basically looking at pre-Bolzano days of calculus, from Newton, Leibniz all the way to Cauchy and Euler. So that is the level of calculus that I would like to discuss as part of this discussion. Okay, we'll start with our function discussion before we get on to algebra of calculus or calculus. Now, what is a function? Function, we say there is one independent variable, dependent variable, and so on. That's one way of looking at it. If you recall, we assume that we are going to represent real numbers with points on a line. So that is there. What we call the x-axis, you can call it the x-axis. So we have different real numbers here. And in fact, we can have even intervals of those numbers from one real number to another one real number, including or excluding the two endpoints. We have open intervals and closed intervals and so on. Now, for each of these, if there is a mapping, so function is actually a mapping. We have the real number set of real numbers, and for each one of them, or maybe not each one of them, at least for some of them. That means basically we are talking of a subset. We are talking of a subset of real numbers, which may actually contain, which will definitely contain infinite number of points, real values, and from each of these we map on to a real number only. That means this maps into real, part of real again. So it will map, probably it's going to map into a subset of the real number system only, real number set only. Now, if you can visualize that, this is actually the mapping. Now, this mapping is known as a function. Normally, that is denoted as f, for short for functions. So this standard nomenclature also. In fact, our friend Euler, I think, was responsible for the standard nomenclature. Something great, Leonhard Euler, you can see he gave us the standard representation for, let me list, what we call f of x, f is a function of the variable x. So depending on the value of x, that means x is taking any value inside this subset of real numbers. This is known as the domain of the function. It's called the domain. Domain is the set of real numbers which you give for this value x, which the x can take, and the corresponding set of values that we get in the function is known as the range. He gave this name, the way of writing f of x, which makes it very convenient. And tomorrow I can have one more function which is g of y. That means the variable y is changing, and you get a mapping whose name is g. That is the name of the function. Very nice name. Then he also standardized the usage of I to represent square root minus 1. He standardized the usage of e for the base of natural logarithms. He used the name pi sorry, to represent the ratio of circumference to diameter of any circle. Pi. That's it became a universal name. Anybody writes pi, we know what we are talking about. Then he standardized the name, this capital delta, to to indicate infinitesimal quantities. That means I want a very small value of x, no? Tiny value of x, you can call it delta x. It's a tiny, infinitesimal value. Infinitesimal is not just tiny. Tiny is some small value, no? Small values, you write them as epsilon or maybe the lowercase delta or whatever, but it's not even just small. It is a 1/1000th of a small or 1/1000000000th of a small value is known as an infinitesimal. No? So that is delta is used for that purpose. Then sigma is used for summation. No? These are all Greek letters. No? Sigma, so it becomes very easy to write, like for example, I can write sigma n where n goes from 1 to m or whatever. Just add a series of natural integers 1, 2, 3, 4 up to m, and the total is sigma n. I can write. Value happens to be m into m plus 1 by 2. Whatever. We know that value. And what about sigma n squared? As n goes from 1 to m. So this is m multiplied by m plus 1 divided by 2. And what is the sum of the first n squares of integers? I don't know if you know it. M into m plus 1 multiplied by 2m plus 1 divided by 6. What about sigma n cubed as n goes from 1 to m? M squared multiplied by m plus 1 whole square divided by 4. The square of sigma n. No? In fact, these three numbers, these three summations were discovered by Brahmagupta. That's why I mentioned it in passing. Not a big deal, of course. But now we come to, if you want a really difficult deal here, we come to one more sigma 1 over n squared as n goes from 1 to infinity. Now you see, it's an infinite series which is convergent, and the value will be, for some reason, our friend pi is coming there, pi squared by 6. So this was proved by Euler. I'm saying it's one of the minor things. He says, Saturday evening, what were you doing? I asked you to come and meet me so we could discuss. 2 hours you didn't come at all. He said, no, I was looking at one small series. I found one interesting value. No, it's not even worth publishing as a paper. So he didn't even bother publishing it, but he just discovered it casually over an evening, evening tea. That's the kind of brain he had. Pi squared by 6 and so on. So sigma, he introduced that. So great fellow. Doesn't matter. Anyway, this I should have mentioned in history, but I always don't miss an opportunity to mention some things which were of great interest to me and inspirational to me whenever I get an opportunity. So I did mention that. So it's fine. So no loss of generality on that. Right. What we should do next is to look at some actual functions and how do we represent this on this plane. No? Now we can treat this plane itself is a Euclid plane where we used to draw triangles and circles. Now we're going to treat that as Cartesian plane. No? Cartesian plane is drop one perpendicular line and call it y-axis. That means for every point here, I can represent a y value, which will be the value of the function. So that means I can plot function f as a graph. It's a graph way of plotting. It's very nice. And if you have continuous neighboring points, we can draw that as a line. So I can have a function like this, or I can have a function like this, with a sudden jump and a break. So when I want to write a function plot, either I can write it without removing the pen from the board. We'd like to call that continuous. It's a continuous line. Or with a break also. So it's quite possible. So this is not continuous. So you can imagine continuous and not continuous. We'll have to give, this is an intuitive way of looking at continuity, but we'll have to give formal definition of continuity. But before we do that, I would like to look at a few functions, simple functions. One function is a mapping, is actually no mapping at all. Whatever you give him, he'll give the same answer. It's a 10. Now you give another real number mapping at 10. You will give the same constant value, which if you plot will be a straight line parallel to x-axis. So this is like a function is equal to constant. We can see that. No? Any value of x the same value of f, that is a constant. So that becomes a horizontal line which is parallel to x-axis. Depending on the c where it is, it can be even below with a negative value of c or above. Or it can be the x-axis itself, which is f equal to 0. So we can visualize that. So the next function we would like to plot is f is equal to x itself. So whatever you give, it will give back as a reply. Like a mirror, whatever you call it. So you say 10 is a 10. You say minus 5, it will give you minus 5. Whatever you give him, it will give back the same. Would be something like a 45-degree line across the origin. Because for positive values, it will give you the corresponding positive value. For negative value, it will give you the corresponding negative value. So you have the negative y-axis also, positive y and negative y. So it will give a 45-degree line. That is f is equal to x, right? Very interesting. Next case, we'll take f is equal to 1 over x. A bit more complicated. So that means as x increases, it keeps decreasing. It will probably hit 0 sometime. So what does that look like? When x equal to 0, obviously it is not defined because division by 0 is not permitted. We call it infinity. Infinity is really not a number, so we can't divide by 0. So at 1, of course, it will be 1, so it will be something like this on the positive side, and there is a corresponding branch in the negative side also. That means at 0 it is not defined, it goes to minus infinity this side. Very small negative quantities, it is minus infinity. Very small infinitesimal positive quantities, it is plus infinity. And others, for infinity on the positive side, it goes to 0 from the positive side. For infinity on the negative side, it goes to 0 on the negative side. So it is both are 0, it reaches 0. This is f is equal to 1 over x, correct? That's also an interesting function. Now one more function I would like to draw. Let me rub this, not to clutter up this diagram. Is known as a absolute function. Absolute function is written as mod x, with 2 vertical bars. That means is absolute distance from 0. Whether x are positive or negative, the value is positive only, so we give that. So obviously on the positive side, we get a 45-degree line, just like f equal to x. On the negative side, it won't be a reflection. It will be a mirror image on the y-axis, also positive. So this line is a f is equal to 1 over x, is one simple function. These are all well-behaved, many of them, most of them are well-behaved functions which are continuous. Now, people, mathematicians, what they want to do is to design, they want to design what are called pathological functions. That means what is pathological is a disease. Functions with a disease, they want to construct. Why is that? Because if you say, I'll give you one theorem on a function, or I can give you one logic for a function, I want to test the logic. How do you test the logic? You use some nice functions, will always work correctly. So I'd like to give you a function with some disease and see how your logic behaves on that pathological function. So pathological function design, mathematicians are there who can design these functions such that whatever argument that you give actually will fail. So they want to be able to construct that. That itself is an art in mathematics. So one simple example of a pathological function is a function with a hole. That means not continuous. So simple way is, I say I got a function, I will write that as in the domain is not the same value for 2 domains. That means I select 2 domains and write 2 different way of giving you the answer. One is, it is, let us say it is 1 value as long as x is less than 0. And we will say it is still 1 only as long as x is greater than 0. That means I got two intervals here. One is x greater than 0, other one is x less than 0. In both cases, the value is the same. But now remember, 0 has not been specifically included in this, in the two sets I given. So there is a hole. So it is a continuous line, parallel line, exactly like f equal to constant. But at the 0, I will show you a hole here. I mean, I can't really, because the next point is there. Now just the next infinitesimally next point on either side is part of the line. There is only one point missing in this entire line, is a break at x equal to 0. Right? It's fine. That is one pathological function. Now the next is known as a step function. Step, it takes a step. Now what is a step? I start off with a value of, let us say 3. Start off with a value of 3 for some distance, and suddenly I decide to take a step to 4. So if you look at a staircase, like this, no? I don't have to write the entire staircase, I'll write only 2 steps of the staircase. That means, how do you write that? Now, the value is 3 if x is less than or equal to whatever this value is, right? This may be 2, okay, 2. And is 4 when x is greater than 2. This is 4. This is a step function. So you can see there is a break there. No? So it's not continuous. So it is a pathological function. And our friend Weierstrass, Karl Weierstrass, was an expert in designing pathological functions. So he could come across with we designed a pathological function which is continuous actually. That means there is no break, there is no hole, there is no step, nothing. Totally continuous at every point in its domain, but is not differentiable at single point in the domain. So you can imagine the complexity of that function. So you could design such a function. So they like I said, pathological functions are designed with that in mind. So this is enough background on functions. Now, if you look at the step function also, f, when I take x, the problem will be with the gap, no? This gap here or this point where there is a break or whatever. So we know that we are almost there, but we are not there. So something like tending to but not touching. So this is something which you have to intuitively understand. Tending to but no touch. That is, but not reaching. This is the same as the tortoise walk that you found, no? Is tending to that point but never reaches that, no? Never touches that. So that is a property of what we call limits. We call it a limit. Limit is it tends to that, but we don't touch it. So, now, how do you specify that? No? These were intuitively assumed by Newton and Leibniz and all the fellows earlier. It required Bolzano to actually give you the correct, rigorous way of writing that limit. What we call the epsilon delta technique of writing. It's only a way of writing, but it helps us understand mathematics with much more rigor. Okay. Let me show that here. The simple example. We are saying a function f tends to a limit L. Read that as an arrow. And why f is changing? Because our x is changing. Original x is changing. As x tends to a real number a, some number a. Doesn't matter what it is. So as we take x and approach a, the f is going to approach L. And it can approach as close to L as you want. Whatever closeness you want, it can approach. Provided x has come to some enough closeness to A. That means the closeness of x to A really depends on how far or how close you want f to become near L. So So now we have two small quantities here, tiny quantities. Popularly, epsilon and delta are used as those quantities. So, in fact, the entire way of writing it is called the epsilon delta method, epsilon delta technique. So, we are saying that this is a definition of a limit. We are saying f as a limit tends to L as x tends to A if for any given epsilon. Epsilon is always given as part of the definition, or somebody can give this epsilon. You can give, for example, 0.01 is a small number. You say, no, I don't like 0.01, it is very big. I will say 0.000001. No, I can add as many zeros I want between the point and the 1 and say that is my small number. So you can define your whatever small number that you want, that is given. Once you give that, now I am saying I will give you the delta for you. So delta basically you can think of it as a function of epsilon, really speaking. If you give me an epsilon which is 0.01, I'll give 1 delta. If you give me an epsilon which is 0.00001, I'll give you a new delta. Doesn't matter. That is, as long as, that is, we say the definition of limit is f minus L is the distance between f and L. No? So, remember, we never reach L. No? It's only the distance, but unfortunately this distance can be positive or negative. So, we take the modulus. Absolute distance between f and L can be made to be less than this whatever small quantity that you specify by saying if 0 less than mod x minus A less than delta. That means I can specify a delta such that as long as mod x minus A is less than delta, that means x is around the delta neighborhood of A. That means if you say A is a point on the real axis, what is a delta neighborhood? Is a delta on either side. No? So this is known as a delta neighborhood. Of A minus epsilon to A plus epsilon, no? that range, that interval is known as the delta neighborhood. So, as long as we restrict the x to delta neighborhood of A, your f will be restricted to epsilon neighborhood of L. And we never need to reach A, so I have written specifically 0 less than mod x minus A. Normally people omit this. It's not good. You should write that 0 less than also. I am saying mod x minus A will never be 0. As far as this test is concerned, doesn't have to become 0. So there is some distance from x to A. It will be made small enough so that f will become as close to L as you want. This is known as defined as a limit. So we say f, we write that f tends to L as x tends to A is way of writing. Other way of writing the same thing is to write that as limit LIM or LIMIT. You want to write the full limit x tends to A at the bottom of y with L. This is how we write that. Limit of y as x tends to A, write that x tends to A below that limit equal to L. So this is the limit. Now obviously when you say, I could have written f here or I have written a y as a function, doesn't matter. Whatever function name that you want to use. So, now when you say I got a function whose limit I know, I got another function g whose limit I know, what about the sum of those two functions? So now we have to combine different functions to see can we find their limits. That means what we are saying is I've got, let's just start a new diagram here. I think that would be a good idea to do that. So basically I have two functions, call them f and g. So I got a function f of x and I got another function g of x. So when I give a value of x, I'll get a value of f from this function, I get a value of g from the other function. I get two values, right? Now we are saying it is given. We know that limit as x tends to one real value, call it a, of f is given as L. I am also telling you a limit as x tends to a of g is another real number, call it m. I got two limits there. Now I am asking you the question, if I add f plus g as a function, then always add. For every value of x, I will get a value of f and a value of g, and I add those two together. I get the sum of this f and g, f plus g, and I want to take the limit of this as x tends to a. Right? What do you expect? This will be L plus m. I mean, that's the theorem. If you want a theorem or a lemma, lemma is limit of of adding two functions is the addition of the two limits. Correct? If you want, you can prove it also. How do you prove it? Because these two statements are given. That means there is an epsilon delta combination which is already given for the f and g. That means for every epsilon that you specify, I can always find a delta. Now I will call it delta 1 of epsilon. For f, that is a delta 1 neighborhood of a for which mod f minus L will be less than epsilon. Similarly, for the same epsilon, I can get you one delta 2, which is actually a value depending on the epsilon. Just call it delta 2, such that by restricting x to be within the delta 2 neighborhood, I can always make g to be as close to m as I want. Now, when you say f plus g, actually we are looking at modulus of f plus g minus L plus m is what we want to restrict to an epsilon neighborhood. Now, that's what we are trying to do here. Saying if you want to say limit of f plus g is L plus m, this is what we have to prove. Now this epsilon. Now I got, when you say minus, I can rewrite this expression as f minus L plus g minus m. Correct? Because I have this f minus L coming out of that first limit, g minus m coming out of the second limit. No? So, but I got two epsilons, really speaking, which I am adding. What you could do is, when somebody gives one epsilon, you just split that as two epsilons by saying epsilon by 2 here and epsilon by 2 here. So, right? I mean, sometimes if it is negative, then it won't even add, but it doesn't matter. Just be on the safer side. Epsilon by 2, maximum value we will get is totally epsilon only. Correct? No? So, as long as we restrict f minus L to epsilon by 2 and we restrict g minus m to epsilon by 2, this will be restricted to epsilon. Correct? Therefore, L plus m will be the limit. Now, how do you restrict f minus L to epsilon by 2? I can always do that. If I can do it for epsilon, I can always do it for epsilon by 2, because that's the definition of these the limits. No? Assume you got a lower limit given, not epsilon, but epsilon by 2 is given. So take delta by 2 if you want, or delta by 10 if you want. Or this delta 2 and this delta 1 may not even be the same. Here, in the case of f, I may have to take half of it, whereas in the case of g, I may have to take 1/10 of it to restrict that to within the half. So what you do as a delta here, you define delta as the minimum of those deltas of delta 1, comma delta 2. Take the minimum of delta 1, delta 2 and say that is my delta. As long as I restrict x to be in this delta neighborhood, we know, because delta is the minimum of these two, f and L will be restricted to epsilon 1 and epsilon 2, which are actually half of epsilon. Their total will be restricted to epsilon. So therefore, the limit of a total is total of limits. Very simple. Now you can do as an exercise, what is the limit for f star g? Product of two limits is the limit of the product. Limit of the product is product of two limits. You can prove that. Should be simple. Not as simple as this maybe, but you can figure out that. Then a difficult proof may be to prove limit of a quotient f by g is the quotient of the two limits. No? Limit of f divided by limit of g. There is of course one caveat always. When you do a division, always the g never goes to 0. I mean, never take the 0 value. Never take the 0 value. Division by 0 is not allowed. But sometimes it is allowed when we divide 0 itself. That means basically 0 by 0 many times as a limit. I'm not saying as a regular value. 0 by 0 is alright because that can be a proper quantity. Whereas anything else by 0 is not valid because it is infinity is not a number. Right? 0 by anything else is fine because that is the value of 0. But 0 by 0 is many times is alright. Or infinity by infinity many times is alright. You understand? Or 0 to the power of infinity many times is alright. Or infinity to the power 0. See, these are all what are called indeterminate values. Because their absolute value is indeterminable. They are indeterminate. But then as limits, you'll always find probably they exist. Now, I'll give one very simple example. Very simple, stupid example I'll give you. Supposing you take a function f, which is x squared minus 1 divided by x minus 1. Simple, right? And I want to look at this limit of this f as x goes to 1, tends to 1. Now when x actually becomes 1, x squared minus 1 becomes 0, x minus 1 also becomes 0. So it is actually the 0 by 0 format, right? So, which is indeterminate, but then as a limit it should really exist. Suppose you take a very small value outside 1, in a small range. I can take some examples also. Supposing x, let's write values of x here. Value of x minus 1 here and value of x squared minus 1. Right. Or I can write x squared minus 1 by x minus 1. You can calculate all these values. Actually compute as long as x is not 1. Then we divide. So x squared minus 1. I want you to do this some computation, some values. No? Supposing x is 1.1, close to 1. I got 0.1 extra. So x minus 1 will be 0.1. What is x squared minus 1? 0.21. What is x squared minus 1 divided by x minus 1? 2.1. 2.1, correct. Supposing you take x is instead of 0.1, it is 1.01 and see 2. We could have calculated that in a simpler way. I think x squared minus 1 is x minus 1 multiplied by x plus 1. Divided by x minus 1. Now, as long as x minus 1 is not 0, as long as x is not 1, x is not touching. Anyway, in the case of a limit, we don't expect it to touch 1. So, since x minus 1 is not 0, we can always cancel that from numerator and denominator, and the result will be x plus 1. It's always x plus 1. You can see that ratio will always be x plus 1, which is 2 in this case, when x actually becomes 1, right? That is, so indeterminate forms, limits do exist. In fact, when you say I want to look at a derivative, to start with, it is an indeterminate form. It's what is known as an instantaneous rate of change. What is the derivative here? Instantaneous rate of change. So now I'll give you the inspiration or the need for inventing calculus. Remember, necessity is the mother of invention. Anything which has been invented in the scientific world, including mathematics and physics, mechanics, engineering, whatever invention man makes, always because of a need. There is a need for it, so they make the invention. So what is the need for calculus is the question. So remember our friend Newton. In the case of Leibniz, I think he had no need to invent anything. Out of sheer academic interest, he was so interested in mathematics, he worked out that. So let's forget about Leibniz for the moment. Just look at Newton. Newton's predecessor, a couple of predecessors, one was Kepler, and before Kepler, Johannes Kepler, we had Tycho Brahe, right? We had these two gentlemen. Tycho Brahe recorded positions of Mars over a period of 20 years. Kepler had looked at those positions and came up with his world popular Kepler's laws of motion, laws of planetary motion. And there are three laws there, just like Newton's laws of motion. There is law number 1, number 2, number 3. Kepler's law also. There is law number 1, law number 2, and law number 3, right? So what are those? If you want, I'll state those. One very simple. All planets orbit in an elliptical orbit. That is the first. It is not circle, it is elliptical. With the sun as one of the focus. Right? Sun at the position of one of the foci of the ellipse. That is the orbit of the planets, all planets. Then the second is planets sweep equal area at equal time. Equal area at equal time. That means, what is the sweeping, So that is, if you take sun, in fact, you take the center of the sun, center. Sun is huge, millions of kilometers in diameter. We take the center point of the sun, and you take the center point of the planet, and you join a line from the center of the sun to center of the planet. This line, if you just visualize, as the planet moves, this line is sweeping this space, It's like a broomstick is sweeping. So it sweeps the space, and the area that it sweeps, that area of that sector, part of the sector, that is equal at equal periods. That means aerial velocity is constant. That's the meaning of this. And third has got something to do with the period of revolution. It depends on the distance. Let me not bother about that. And Newton, when he looked at this why should equal area be swept at equal points? His fundamental thinking for calculus started with that second law of Kepler's motion. So we'll not worry about these as planets. Let's just take any two objects. So Newton said, let me take 2 points here. Something very simple. So I got one point here. We can call it O. This is the sun actually, origin. Right? And I got another point here. To start with, we'll put it on the horizontal line, on the x-axis. And now this is going to move around as an ellipse, right? So actually, if it were not to move on an ellipse, what would it have done is the question. So it would have gone in a straight line. So anything moving straight, Newton's law of motion is there. Undisturbed, a body moving in a straight line will continue to move in the same straight line at equal speed. So we'll follow that. Let us assume planets also follow the Newton's law of motion. So that means this should have gone straight up, correct? To a distance. Unfortunately, this planet has not done it. It has actually travelled in an elliptic or circular orbit. I have to draw this in a very small, narrow part, but I have drawn it big for you to see it actually. It's a tiny distance that I have shown, right? So that means, in the tiny distance, what is the distance it has moved towards the center? Towards the center is not this angular line, because I am really drawing this very close to the first point. Second point is very close to the first point. So the horizontal line is actually towards the center. Sun is so far away that is actually practically parallel, parallel to this line. So these are. So planet has reached here instead of here, correct? So now, if it had not done it, that means not moved it, what would be the area that it would have swept? Area of this triangle, correct? No? It would have swept the area of this triangle if it had not moved away from this straight line, right? Now, what is the area now it has swept? It is the area of this triangle. It is actually not a triangle, it is a curve. But then if you make it small enough, it will become it will look like a triangle only, right? So now I got two triangles here, right? On the same base, same height. And what are their areas? You have seen in geometry, they are equal, no? They are equal area. So it has swept the same area. So whether it goes straight ahead or it travels slightly to the center, it sweeps the same area. So follows the Kepler's second law of planetary motion, correct? So now only the question now has to be answered by Newton. Why did it move towards the center? That means we find actually planets are not going around in a circle or ellipse. Really they are going towards the sun, no? You understand? They want to go towards, they are going in their own direction, some direction they want to go. But in addition to that movement, they also happen to be going towards the sun some distance. No? And that is what is our old fellow said, Guruttvaakarshanam. Sun is so heavy. Sun is so heavy, it attracts other objects in space. And that is Akarshanam. Akarshanam is attraction. Guru is a weight. Weight attracts. No? So that's the law of gravitation. So Newton said there must be a force which the sun is exerting at that distance to attract these planets. So it is pulling them to itself. Actually, it's not going any other place. And because they happen to go in a straight tangential direction, this pulling will result in the actual elliptical orbit, which Kepler has so nicely written and documented and is correct. Kepler's law of motion is perfect. And how we explain it is by law of gravitation. Now to do that, now we have to really say, is that really correct? I mean, what is that force? What is that Guruttvaakarshanam or gravity or force of gravity? In English, you write that as force of gravity. This is the English translation. So what is that force of gravity and how much is the force of gravity becomes the question. No? So, and to study that, you have to look at a tiny piece of that movement and study how much it moved, how much this fellow didn't move, and what is the force which got applied. We have this on Earth. We had that Newton's laws of motion. No? They are already there. Law of, what do you call them? Laws of motion. And there also we got three laws. No? Object at rest remains at rest. Object at constant speed continues at constant speed. And then what is the third one? When you apply a force, it introduces an acceleration which is proportional to the force. And that force is equal to mass multiplied by acceleration. So when you apply a force, depending on the mass, it reaches an acceleration which is m. And acceleration A is actually F by m, right? So force divided by mass of the object will be the acceleration reached by that object. So when you push an object, that is the acceleration we are imparting to that object. So now you can see that if that is the case, and we are having a force which the sun is exerting on the planet, there must be an acceleration towards the sun. No? We can calculate the force. That we have to do tiny calculations, and the existing algebra of Al-Khwarizmi and Brahmagupta are not enough for that. Algebra, you can't do those calculations. You need to invent something new in mathematics. To do these tiny calculations where everything is not quite touching but can touch. See, that limit business is there. So we have to get into those limits of things. For each movement, I want to look at this planet after 1 microsecond and see what it has done. How much got exerted, how much force, how much movement, how much distance, how much area, everything. I want to calculate tiny distances, tiny times. And Newton's unknown variable or the primary variable always time. He always looked at time as the primary variable. You can call it t. What we are using as x here, f of x. Newton looked at things as y of t, or x of t. Always his functions. He didn't write it as x of t. He just wrote x. When he writes x, what is x? X is x of t at a point of time. What is the value of x? That is where is the planet at that point of time. After a little more time, what is the value of x? That is where the planet is. So x of t, y of t. So he always. Now how does x change? X change with respect to time. So now there we have, of course, we have the second law of Newton's law of motion, at uniform speed. So one is speed. So first, with respect to time, how does the position change? So we are looking at the position of an object which changes with respect to time. So it's a function of time, correct? Position as a function of time is what we are looking at. And the first change of position comes because of speed, what we call velocity. And it will be normally constant. As you know, Newton's law states velocity doesn't change by itself. No? So velocity is constant. That is the rate of change of position with respect to time. No? So if you give 1 hour, it travels so much of distance. You give 2 hours, it travels exactly twice the distance. Half an hour, half the distance. 1 microsecond, 1 micro ratio of distance. So it is distance is proportional to the time. No? That means you can write that as S, which is the distance travelled, is equal to the speed multiplied by time. S equal to ut. Simple equation, right? U is the speed or velocity. Speed and velocity are approximately same, except that velocity also indicates the direction. Speed is just a number. No? So velocity is speed with the direction. It's called velocity. U is the velocity multiplied by time period will give you the distance travelled. So S is the distance equal to ut. Very simple with the velocity. But then now you come to acceleration. When you push that object with an acceleration, we are changing the velocity itself. And that velocity change is not constant. That changes every tiny period of time also. Every infinitesimal amount of time, velocity is changing, is continuously changing. And that is the next level, is known as the acceleration. Acceleration is a steady increase in velocity. Increase or decrease. I'll write it as increase. Steady increase with respect to time of velocity is known as acceleration. That means velocity is 10 miles per hour now. After 1 hour, it becomes 20 miles per hour. After 2 hours, it's going to become 30 miles per hour. So steadily, the same rate it is increasing. That is known as acceleration. Now, with respect to an acceleration, we can call it A as acceleration. Now, you can calculate what is the distance travelled and what is that. S will be, of course, it also had the original speed, so there was an ut component there. Plus, because of this acceleration, it will travel an additional distance of half at squared. So, ut plus half at squared will be the distance travelled in the case of acceleration. Okay, we have seen that in Newton's laws of motion. That is fine. What about supposing I change the acceleration itself? There is an instantaneous rate of change of acceleration. It doesn't happen in the case of planets, but then it might happen. No? So we are looking at the next. What is the steady increase of acceleration called? What do you call it? It's called a jerk. In fact, the name also suggests if you are driving a car, one is steady speed, very smooth, no movement. Now you can see when you are sitting in the car, there is absolutely no disturbance, very quiet. No? Whereas when you accelerate, you get pushed. You can see that you get pushed back. That is the Newton's third law of motion. Action and reaction are equivalent opposites. So when there is an acceleration only, you get pushed back. No? That is there. But then bad drivers, if you have got a bad driver when he's pressing the accelerator, there is a jerk. That acceleration should be smooth. Then you will find smoothly you get pushed back. Whereas if it is not smooth, acceleration itself is changing. You get a jerk. So that is known as a jerk. And I can have a steady increase of jerk also. The next level of rate of change is known as snap. And the snap is something like this. This is a snap. This has got a rate of change of jerk there, actually. That's why that word has been used. And what about if I do a snap also I change with respect to time is called a rattle. I don't know why it should be called rattle. Rattling, that rattling is that noise that you produce is a rate of change of snap, which is got a rate of change of jerk, which does the rate of change of acceleration, which change the rate of change of velocity, which indicates the momentum. That's the fifth level. And one last level normally we use in the English language is called it is soda pop. Now we had this old goli soda, that marble soda, where you press that marble, it opens actually with a loud noise. I don't know how we can, I can't reproduce that noise. It's called a pop noise. Now pop, it pops up. The bottle when it opens up, is called a pop. So we have the 6 stuff. In the case of planetary motion, there are only 2 here, velocity and acceleration. But then it is possible in real life. We have seen, I have shown you what is a jerk in the driving of a car and so on. This might be of some interest, at least academic interest, if not more. But Newton was primarily interested in the first 2 because he wanted to solve this Kepler's laws of planetary motion once for all and decide what is this gravitational force which the sun is exerting on Mars. That is the first question. Then if you say sun is exerting it on Mars, why won't it exert it on Mercury or Jupiter or Venus? I think it should be the same, no? Why it is doing that I don't know why, but he is doing it, So. And that next question for answer, you have to wait for another 300 years, 250 years. Another, I don't know, you want to call it brilliant is not sufficient. Everybody is brilliant in that list I wrote. And what do you call Einstein? I don't know, just calling him brilliant is doesn't justify his contribution to physics. Einstein had to come after 280 years and give a possible explanation. It's not 100, nobody is 100% certain. Possible explanation of why gravity should be there on his theory of relativity. Correct. That is fine. Newton said, no, I don't know why sun should do it, but at least let me figure out what it is doing and write down for it. And he came up, instead of 3 different laws of Kepler's laws of motion, he came up with a single law of gravitation. He called it universal law because the sun is doing on this, therefore earth also must be doing it on the moon, obviously. Now I come to realize we are all idiots. What is a tide? Yeah? What is tide? In sea you see tide. No, tide is, you find lot of water coming as waves towards the shore. No? You keep seeing it. What is the meaning of why tides happen? Suddenly water is going up and coming down like this. Why is that happening? Now I know, man. It is because of gravitational attraction from sun and the moon in the night. Moon itself is a huge celestial body. May not be as big as Earth, but it's quite big enough. Sun is of course huge. So what happens? It attracts. It is having an exertion, and water has got a free movement. Sea water has got free movement, so it rises up towards sun in the center of sea. Everywhere it rises up like this towards moon or sun, whichever is there in the sky. And then when Earth rotates, remember Earth is rotating on its own axis. When it rotates, what happens? That attraction point, now you can see shifted there. And this much of water, now it doesn't have the same attractive power, has to fall down, right? And that comes back down as a tide. So they are the tides of sea, which is a result of these. So gravitational attraction is there. Why it is there, I don't know, but it is there. We have seen it in tides. We are seeing it in planetary motion. And to explain that and to calculate exactly, I want to compute, I want to calculate this. I want to do these infinitesimal calculations I want to do. Was a need at that time for Newton. He didn't want to do anything with mathematics. Actually, he is not interested in mathematics. He was interested in planetary motion only. But because of that, he had a need for it, and it is not there. There is no book available, so you have to do the research yourself. So he invented that calculation, and that is calculus. And he did that, most of it through intuition only, so it was not really rigorous. Even our friend Leibniz also did that instinctively, guts. I got a gut feeling this is what it should be. I got a gut feeling Shastry passed through that door before he went to the other side, and so on. Didn't disappear from here and appear there suddenly. It's a break-in function, no? So it didn't happen. So that's what Leibniz also did. That's why I say rigor was not there in those days. It was introduced later by our friends we had Cauchy to start with. And Cauchy, like Euler, did so much of research, may not be as much as Euler, but maybe half of Euler. Even he didn't have time for this rigorousness so much. So he commented on rigorousness of Newton and Leibniz, and his own work also lacks some amount of rigor, which was corrected later by our friends Bertrand Bolzano and Weierstrass and company. And I suppose there are other mathematicians in that list, but those whose names I picked up because their thinking style is sort of unique, so you can't imagine, that kind of thinking level. What you saw in Euclid for geometry, what Euclid did for geometry in his axioms, you can see is something fantastic, that kind of fundamental thinking that has gone into that. So we'll start with, we are not going to do Bolzano calculus here. I'm sure that's not part of your syllabus. We'll do Newtonian calculus only, but with nomenclature, which is a epsilon delta notation, all that is very nice and smooth. So we use that and start doing some derivations. What is, you've got a function x squared, what is the derivative? We have to first define derivative. We've not yet done that. Before that, we have to define continuity. We only have seen limits. So we start with continuity, then derivative functions, then first order, second order, third order, right? Brahmagupta had already seen second order derivative and used that as an approximation for sine, right? But it went nowhere, because either it got missed in translation by one of those translators, or they didn't even see the importance of it. Many times translators say, what is all this? Who wants this guru? I can't even pronounce it. It's not interesting. This decimal is very interesting. So he missed this. Totally he missed that. Probably he missed that term, no? Gurutvakarshadam was totally missed by these people. Possible. We don't know the reason. We don't know what went into their thinking process. We won't know for sure unless you study the original Sanskrit in poems. You should have a thorough knowledge of Sanskrit. Second, study the actual translation to Arabic, so you should know Arabic thoroughly. And third, you should know Latin. All three languages, if you know thoroughly, then probably you can figure out who missed what in those translations. So that itself is a research, because many of the historians today spend their time trying to figure out, did Newton go there in the evening or he went in the morning? No? So I want to find out, Correct, no? So it's very interesting. So somebody can take it up. I don't know if it is interesting. Somebody can take it up. So we'll start the next topic of discussion with continuity. I think that is a topic. We should start with that. Necessity was planetary motion, as you know, for Newton to have invented all those mathematical subjects, even though his primary interest was in physics. Okay.